Hello, welcome back to the short lectures in physics. And the topic for discussion is the dispersion of light. Dispersion refers to separation of white light into its constant colors while passing through a refracting medium. When a narrow beam of white light enters a refracting medium, it undergoes deviation and splitting. Deviation is changing its path direction, and splitting is separation of the white light into different colors. Angle of deviation is the angle made by the emergent ray with the incident ray and is the overall refraction that is occurring in the process. The angle of deviation is different for different colors. It's known that light waves travel slower in a medium that is having a larger refractive index, because refractive index is a ratio of velocity of light in medium with reference to vacuum. And higher frequency, that is lower wavelength violet light, travels slower as compared to the lower frequency, that is larger wavelength red light in a given medium. Light with different frequencies hence refract through different angles. Higher frequency, that is lower wavelength violet light, bends or that is refracts more than the lower frequency larger wavelength red light. And dispersive power of a refracting medium is its ability to resolve, that is separate a white light into its constituent colors. Consider a prism on the slide shown as XYZ, which is a portion of a solid transparent medium like glass bounded by two plane surfaces xy and xz. Yz is the base. The xy and xz plane surfaces act as the refracting surfaces. That means the light enters at one surface and leaves from the other surface. The angle between the two plane refracting surfaces, that is xy and xz, is known as angle of prism, denoted as A, capital A. Let a ray PQ enters the surface xy and emerges out from the other surface xz as the ray RS. The medium within the prism of glass material is denser as compared to the outside medium, air. Angles made by the beams at the xy and xz surfaces are measured with reference to normals drawn to the respective plane surfaces, like TA and TB as shown in the figure. Here you can see PQ ray is entering and incidenting on the surface xy with an angle of incidence I1, and then getting refracted at the point Q with a refracting angle R1 into the prism material, and travels as QR within the prism. At the point R, it again refracts as it enters the air medium and travels as RS as the emergent beam with the angle of emergence I2. A is the angle of the prism. Considering the refraction surface xy, I1 is the angle of incidence, R1 the angle of refraction. Similarly, for the surface xz, I2 is the angle of incidence and R2 is the angle of refraction. Angle made by the extended incident ray PQUV with the extended emergent beam URS is called the angle of deviation, denoted by small d. This angle of deviation d varies with the angle of incidence I. That means it is a function of I. As I varies, the deviation varies. The angle of deviation d variation is shown as a function of angle of incidence in this slide. Here you can note that refraction through a prism is different from that through a parallel sided glass slab. Incident ray and emergent ray are parallel in the glass slab, and the emergent beam is slightly displaced laterally from the direction of the incident beam. No dispersion can be seen in the parallel sided glass slab refraction because the angle A is 0 in that case. In prism, it is not the case like that. The emergent beam deviates from the direction of the incident beam through an angle d. Deviation produced in prism depends on the angle of incident I, angle of prism A, and refractive index mu of the prism. For a given prism, the angle of deviation depends on I, means A being constant. From the variation of angle of deviation with the angle of incidence, we can note that as the angle of incidence increases, the angle of deviation decreases first to a minimum value dm indicated in the slide and then increases again. Thus, there exist two angles of incidence for any angle of deviation except for the one at which the angle of deviation is minimum. The minimum value dm is called the angle of minimum deviation. In the minimum angle of deviation condition, the angle of incident is equal to angle of emergence, that is I1 is equal to I2 as shown in the slide, and R1 is equal to R2. Because of this situation, the refracted beam within the prism material, that is ray QR, travels parallel to the base of the prism YZ. So let us see some results in dispersion occurring through a prism. From simple geometry principles with reference to figure, angle of prism A is equal to 180 degrees minus theta, where theta is the angle between the extended incident ray and the emergent ray. But theta from the triangle QRT, you can represent it as 180 minus R1 plus R2. So the angle of prism A becomes R1 plus R2. So angle of deviation D is equal to difference between I1 R1 plus difference between I2 R2. That is D is equal to I1 minus R1 plus I2 minus R2. That is I1 plus I2 minus R1 plus R2. That is I1 plus I2 minus A, because R1 plus R2 is A. Just above it is shown. So the refractive index of the prism mu is equal to sin I1 by sin R1 is equal to I1 by R1 for small angles up to 10 degrees. Thus I1 is equal to mu times R1, and similarly I2 is equal to mu times R2. So A plus D becomes I1 plus I2 is equal to mu times R1 plus R2. Again R1 plus R2 is A, so is equal to mu A. Thus angle of deviation D is equal to mu minus 1 times A. So this suggests that angle of deviation D depends only on the angle of prism and the refractive index of the material. Let us understand about the prism formula. We have A plus D is equal to I1 plus I2 and A is equal to R1 plus R2. Let I1 is equal to I2 is equal to I and R1 is equal to R2 is equal to R in the minimum angle of deviation condition, where angle of incidence are same and angle of refractions are same. Thus R is equal to A by 2 and I is equal to half of A plus dm. Thus minimum angle of deviation dm is equal to 2I minus A. Then refractive index mu is equal to sin A by S sin R is equal to sin A plus dm by 2 by sin A by 2. This relation is known as the prism formula. Light ray entering the first surface xy with 90 degrees angle of incidence I1 results in maximum deviation in a prism. So maximum deviation D max is equal to 90 plus I2 minus A angle of the prism. Now let us see about a dispersion of light, that is separation of light into different colors. When a narrow beam of white light enters one of the refracting surfaces of a prism, then it gets split into 7 colors as it emerges from other refracting surfaces. Splitting of a white color light beam into 7 colors as it travels through a refracting material is called dispersion. Colors seen from base of the prism will be in the order violet, indigo, blue, green, yellow, orange and red. We know this sequences with GR. This sequence of colors is a spectrum of white light. You can see this in the clearly in this figure. The ray PQ is entering the refracting surface XY with an angle of incidence I and getting refracted with the different angles depending on the color of the splitting of white light. and again leaves the refracting surface xz at some other refracting angle, and on the screen you can see the different colors on the top being red, bottom being violet. That is dispersed beam on the screen. The refractive indices of air mu1, refractive index of glass material is mu2. So mu1 is less than mu2. Wavelength of colors seen in emerging beam ranges from 4000 angstrom units to 7000 angstrom units. So 4000 angstrom units is for violet color and 7000 angstrom units about is for red color. The frequency of violet color is more than that for the red color. Reverse is the wavelength. Color of light depends on its wavelength. According to Cauchy's formula, refractive index of a material and wavelength of light are related as refractive index mu is equal to A plus B by lambda square plus C by lambda to the power of 4, where A, B and C are constants for the material under consideration. Also for small angle prism, D is equal to mu minus 1 into A. It will be noted that the spectrum cannot be seen if the prism happened to be hollow instead of a thick solid glass piece. That means if you take a hollow prism that is just connected to glass plates and try to see the dispersion, it is not visible in that particular. The material must be thick, hollow, then is homogeneous glass medium is required. Thus, refractive index mu will be less for light with a greater wavelength like red color. Mu being less for a given prism angle A, deviation D will be less. Mu less, deviation will be less. Thus, deviation will be less for colors with the larger wavelengths like red, and will be more for smaller wavelengths. That's why the violet color light is seen close to the base of the frame, being refracted to greater angle than that of the red color. Wavelength of each color is different for different refractive materials with reference to A. Now, angular dispersion is the angular separation between the two extreme colors, means top being red, bottom being violet. The angle of deviation differences between these two colors is known as the angular dispersion. The angle of deviation for violet color, that is dV, is given by mu v minus 1 into A, while for red color dr is equal to mu r minus 1 into A from the formula we just now noticed. So angular dispersion is the difference between these two angles for violet and red color, that is dV minus dr, that is equal to mu v minus mu r into A. So the angular dispersion also depends on the angle of the prism and the refractive indices of the material, prism material. Difference in refractive indices of the two extreme colors mu v minus mu r may be taken as the refractive index of the mean yellow color. Ratio between the angular dispersion with the deviation of the mean ray. That means we have extreme colors red and violet, and the central color is yellow. So the ratio between these angular dispersions for these combinations is called dispersive power, that is omega of the prism. It represents the ability of the prism to resolve the white light into different colors distinctly. So the dispersive power omega is equal to dV minus dr by d, where d is the mean deviation for the yellow ray. But dV minus dr is equal to A into mu v minus mu r, and d is equal to A into mu minus 1. Thus dispersive power omega is equal to mu v minus mu r by mu minus 1. Thus a white light passing through a prism undergoes deviation and dispersion. We have seen both occurring, that is deviation from its path as well as separation of white color into different colors, that is dispersion. Both are seen when a white light is passing through a prism. It is possible to get deviation without dispersion or dispersion without deviation by the combination of two prisms having different refractive indices with a suitable angle of prism values. They must be arranged such that their bases face opposite to each other. If the combination of prisms result in a zero angular dispersion such that the light beam entering one prism, say crown glass, crown is the material of the prism, leaves the other prism like a flint glass with only deviation but no dispersion, then such a combination is known as achromatic combination of prisms. In this, the dispersed components of white light in one prism gets refracted and meet together at the outer surface of the other prism. Thus, the emergent ray from such an achromatic combination of prism is again a white light with some deviation. These hydrogen atoms emit light at certain discrete wavelengths as given below. Red light 6560 angstrom, blue light at 3 angstrom, 4860, 4340 and 4100 angstrom. If the light coming from a star produces lines any of these four wavelengths through dispersion, then it confirms that hydrogen gas is present within that star. So the radiations emissions by the stars can be studied to find out the hydrogen presence in the particular star. Hope this finds useful to you, um, and see you in the next lecture with some other topic. Till then, bye.